In this video, I'll be going over the Test 3 review, and this covers chapters 2 and 3. So let's look at number 1. Determine whether each set is well defined. Right, yes, or no. So well defined means that the contents of the set or the elements of the set can be clearly determined. So for A, it says the set of community colleges in the state of Texas. Now we don't know exactly what those are, but we could look this up, and there's certainly a set number that's clearly understood, and so that would be well defined. So we would say yes. On part B, it says the best 3 teachers at Brookhaven College. Well, this is an opinion, not a statement. And so this is not well defined. Let's see, number 2 says write each set in roster form. So on the first one, if you read this, this is set builder notation. This is the set of elements x such that x is an element of the natural numbers and x is greater than 5 and less than or equal to 100. Basically, x is between 5 and 100, not including 5, but including the 100. So in roster form, we would start with 6, 7, and 8, and then we'd do our ellipsis, the 3 dots. Notice we're not including 5 because it doesn't have an equal symbol by the 5. And then 100 is included because there is an equal sign there. So on part B, it says the months between May and August. Now remember, in mathematics, between means in between, and so we can't include May and August, so this is just going to be June and July. All right, let's look at number 3. Now letter A says the set with 6 in it is an element of 1, 2, 3, 20. So the numbers from 1 to 20, the natural numbers. Now be careful here because 6, it would be correct to say 6, whoops, did I mess that? There we go. 6 is an element of that set, but it would not be correct to say the set with 6 in it is an element. Now I could have said subset here, but that's not what we said. So this is a false statement. So be careful. An element or member is just one of the numbers in the set. It's not actually a set itself. On B, it says if A equals the days of the week and B is equal to the even numbers from 2 to 14, then A and B are equivalent sets. Now be careful. Remember, equivalent does not mean equal. It means the sets have the same number of elements. So let's count how many elements are in set B. So I wrote them out, and there's 7, just like there's 7 days of the week, and so this is a true statement. Both sets have the same number of elements. All right, let's look at C. It says the set with D, E, F, and G in it is a subset of the set with A through F in it. Well, let's see. A subset would indicate that each element in the first set is also an element in the second. Well, D is in the second set, D, and that's true for E and F, but what about G? Notice G is in the first set, but it's not in the second, so this is not a subset. This would be false. So every element in the first set has to be an element in the second set in order for this to be a subset. On letter D, it says the set with 3, 4, and 5 in it is a proper subset, and basically if you read that, that's the natural numbers that are less than 6. Well, that'd be 1, 2, 3, 4, and 5. And so remember, proper subset is just like a subset. The only difference is you can't be equal. Well, these two sets are not equal, and 3, 4, and 5 are in the second set, so this is true. Each element in the first set is also in the second. On E, it says 21, hold on just a second, is not an element of the set of basically numbers that are multiples of 3 from 3 to 30. Well, 21 would be in there because 3 times 7 would be 21, and if you're counting by threes, you do hit 21, so that would be a false statement. On F, it says the empty set is a proper subset of any set, including itself. Now you got to think carefully here because we've discussed the fact that the empty set is a subset of every set except itself. Well, actually, it's a subset of every set, but it's not a proper subset of itself because, remember, to be a proper subset, you can't be equal. So we can't say that the empty set is a proper subset of the empty set, and so this is false. G is true because every set is a subset of itself. Letter H, we have the set with 3, 7, and 12 in it is equal to the set with 7, 3, and 12 in it. Now remember, equal sets have the same elements. In fact, you can repeat numbers, you can change the order, but it's still the same set of numbers. And so these are equal sets, so that's true. On number 4, it says, list all the subsets for the set with 1, 2, and 3 in it. Well, let's go ahead and get started by first, we know the empty set is a subset of every set, and we also know the set itself is a subset of itself. So now, let's see, what about the sets that have just one element in them? That would be 1, 2, and 3, the sets that just have 1, 2, or 3 in them. And then we could have subsets where we have 2 of the numbers, so 1 and 2, 2 and 3, or 1 and 3. So that's all the possibilities. If you count those up, there's 8. Now, this is an easy way to check to see that you got them all, is to actually find out how many there should be. Remember, there's a formula that tells us there should be 2 to the n power sets or subsets, where n is the number of elements in the set, and in this case, there's 3 elements in the set. So 2 to the 3rd power is 8, and so we should get 8 subsets, and that's exactly what we got. So make sure you know this formula 2 to the n, where n is the number of elements in the set. It tells you how many subsets there are. If you want to know how many proper subsets there are, you just would subtract 1, because you couldn't include the set itself. All right, let's move on to number 5. Number 5 is a really easy problem if you just know the notation. It says find the cardinal number of set A if A is the set with 4, 8, 11, and 17 in it. Well, the cardinal number of set A just is the number of elements in set A. Well, there's only 4 elements here, so the cardinal number of set A is 4. All right, let's move on to number 6. So we've got a universal set and sets A, B, and C, and we're supposed to find, we have 4 questions to answer here. For the first one, we have to find C prime or C naught, the complement of C. So remember, the complement of C includes everything in the universal set that's not in set C. Well, set C has A, E, and G in it. A, E, and G. And so basically, everything else would be in C prime or C naught. So let's go ahead and write that down. That would be B, C, D, and F. All right, let me erase this here. Okay, and then A union B, remember A union B is going to include everything that's in A and everything that's in B, or what's in both. So I like to think of it as combining the 2 sets together. So what I normally do is I start by writing everything down from A. That would be A, B, C, and D. And then I would add to that anything from B that I don't already have. Well, notice B has E and F, which we don't already have. So A union B is A, B, C, D, E, F. All right, let's look at C. So we're supposed to find the complement of B intersect C. So B intersect C is in parentheses here. We're going to first find B intersect C, and then we can find the complement. So when you do problems like this, you want to take it step by step. So B intersect C is what the two sets B and C have in common, or they're the elements that are in set B and in set C. Well, let's see. If you look at B and C, the only thing they have in common is E. And so basically we're going to write down the universal set except for E. So A, B, C, D, F, G. All right, D, we have A intersect C prime, or C complement. All right, so I think it would be, well, let me go ahead and write down set A. Actually, let's do C prime first. So C prime we actually already found in part A, so that's B, C, D, and F. So now we're going to union or intersect that with set A. So basically these two sets, we want to see what do they have in common. Well, let's see. We've got B and C and D. All right. Let's move on to number 7. It says determine whether, this is the symbol for subset and proper subset, each of those. So the symbol for subset, the symbol for proper subset, both or neither can be placed in the blank to make the statement true. So look at A. We have two equal sets. They have the same elements in them, Larry, Curly, and Mo. So these are equal sets. Now remember, every set is a subset of itself, so we can certainly use the subset notation, but we can't use proper subset because they're equal. And actually it's very similar in part B. These are both symbols that we use to represent the empty set. And so we can use subset, but we cannot use proper subset since the two sets are equal. So just remember, it is possible if one set is a subset of the other and they're not equal, it's also a proper subset. All right, let's look at number 8. It says construct a Venn diagram illustrating the following sets. Well, let's see. The universal set has C, D, G, H, K, U, and X in it. Set A has D, U, G, and C, and set B has X, G, H, and U. All right, so this is a Venn diagram with two circles. So when we construct a Venn diagram in a situation like this, we talked about how you work inside out. So we're going to start in the overlap, or where A intersect B is. So what are the elements that are in set A and also in set B? That would be U and G. So U and G go in the overlap of the two circles. Now let's look inside of circle A. Now we already have U and G in there. So notice set A also has D and C in it. So we should be putting D and C in set A where there isn't overlap. Now let's look at set B. Set B has X, G, H, and U in it. We already have U and G, so we're missing X and H, which go in the circle B where we're not intersecting circle A. And then finally, don't forget, we have one other region that's out here in the universal set, not including what's in the circles A and B. So notice if you look at the universal set, we are missing K. So everything in the universal set should be represented in our Venn diagram. All right, let's move on to number 9. It says use this Venn diagram which describes the optional features ordered by new telephone customers in one day to answer the following questions. So we have a circle for caller ID, and we have a circle for call waiting, and the universal set is telephone customers. So how many customers did not order call waiting? Well, those would be the people that are not in the call waiting circle. So there's 77 plus another 21. And whoops, let me erase that. And so that would be a total of 98. How many customers ordered caller ID? Now, if you're in the caller ID circle, then that means you ordered caller ID. So that includes not just the 77, but the 17 that also ordered call waiting. And so we're going to add 77 and 17, and you get 94. It says Steve ordered caller ID and call waiting, in part C. Put an X in the region that Steve is in. Well, that's where the overlap is, which is where these 17 people are. Let's move on to number 10. It says, in a survey of 50 college students, it was found that 28 have a math class, 21 have an English class, and 15 have both a math and an English class. So we're just basically going to fill out this Venn diagram, and then we'll answer question B. All right, so what we learned is, again, we want to work inside out when we build a Venn diagram like this. So first of all, let me label the circles. We have the math circle and the English circle. And we want to put in the 15 that took math and English in the overlap. So now when it says 28 have a math class, notice in the math circle we already have 15. So if you do 28 minus 15, there's 13 that go on the math circle where we don't overlap. And then in the English circle, there are 21, but we already have 15 in the overlap. And so 21 minus 15 is 6. So there's 6 that are in the English circle where we don't have overlap with the math circle. So finally, don't forget we still have the region outside the circles. So if we add up 13, 15, and 6, we get 34. Remember, 50 were surveyed. And so if we take 50 minus 34, that leaves 16 here. All right, let's go ahead and I'm going to stop this video here, and I'll do a second video.